This video we're going to let t equal to tangent of x to evaluate the given integral. Starts off like a standard trig substitution, but usually in those you don't have the actual functions involved. Usually you have a square root of a difference of squares or sum of squares. What we're going to do is transform this integral, the integrand, into a rational expression using this substitution. I'm also going to look at a shorter method, just in case you want to see another way to do it. This method is a little bit longer, but it's just something new to look at. You might need it when the shorter methods won't work. So here's what we have. We have t equal to tangent of x. That's my main substitution. dt equals to the derivative tangent is secant squared of x dx. And then sine of x. Here's the triangle. The tangent is opposite over adjacent, so tangent of x is t over 1. That's where the substitution comes from. T equal tangent of x is just t over 1. And then the hypotenuse of this triangle is the square root of t squared plus 1. So you can see here that the sine of x is opposite over the adjacent. Opposite over the hypotenuse. So it's t over the square root of t squared plus 1. The cosine is the adjacent over the hypotenuse. That's 1 over the square root of t squared plus 1. Now in the integrand we have sine squared and cosine squared. So if you square this expression here, it's going to give you t squared over t squared plus 1. The radical is gone. Cosine squared, if you square this out, is 1 over, square the denominator, you get t squared plus 1. So here's what we're going to do then. Secant squared, of course, is the hypotenuse. It's opposite of the cosine. So is the hypotenuse over the adjacent side. Square root of t squared plus 1 over 1. So that's how we get this for the secant squared. So we have a dt in the integral, or dx I should say. The dx is going to be replaced by dt over t squared plus 1, the dx. The sine squared will be replaced by this quantity squared. The cosine squared will be replaced by this quantity squared. So make a note of that. So let's start with the process here. This will be the integral, and dx from right here will be dt. So let's do it this way. The dx here, divided by t squared plus 1, is replaced by dt over t squared plus 1. So now here we're going to have 4, and then it's sine squared. So here's sine squared right here. You square it, and that'll give you a t squared. So it'll be t squared over, and this one will get squared. So that's going to give me just t squared plus 1. And then it's plus cosine squared. So here's your cosine of x. Square it, and you get 1 over t squared plus 1. So this will be 1 over t squared plus 1. So see what happens here? When we do the substitution, it's going to give me a radical expression here. So multiplying by the t squared plus 1 is going to cancel, see, in the denominator. This and this are going to cancel, and I'm going to have dt in the numerator. In the denominator, I'm going to have this 4t squared plus 1. So after making the substitutions and simplifying, we get the integral dt over 4t squared plus 1. And then this right here can be replaced by 2t quantity squared. So we have it like this, 2t quantity squared plus 1. Now I could apply the theorem that leads to the arctangent here. But so it's clear here, I'm going to use another substitution here. I'm going to let u equal to 2t. Then du, derivative on the right with respect to t is 2. And then this will be dt. Divide by 2 here. And now the dt is replaced by du over 2. I put the 1/2 on front here. And then this gives me the integral of du over, that's your u there, u squared plus 1. And I just used this integral in the last, or this formula I should say, in the last video. So I'm just going to give you the answer here. This is going to equal to, whenever you have this format here, du over u squared plus 1, well, the constant's going to stay there, so this will be 1/2. Any integral that looks like this has a value that's arctangent or tangent inverse of u over a. And the formula, this is a squared here, which in this case is 1. So this is 1 squared. So the formula tells you that if in this format, it's 1 over a. Well, the coefficient would be 1, and then a is 1, so it's going to be 1. And of course, the 1/2 comes along for the ride. So it's 1/2 of arctan of u over the a. Remember, a is 1. So u is what? Was 2t, right? U is 2t right here. So it's going to be 2t over 1, which is going to be 1. But what is t over here? Got to go back to the original variable. T is tangent of x. So this would be then 2 tangent of x. So final answer then again is 1/2 arctangent, or tangent inverse if you want, of 2 tangent of x, and then of course plus your constant of integration. So we started off with the substitution of t equal to tangent of x, and from that information we got this triangle. So again, just in case it's not clear, this is over 1 here, so form the triangle. Tangent of t over 1, or tangent of x, is equal to t over 1. So set it up. This will be the angle x. This is t. This is 1. Tangent is opposite over adjacent. And then using the Pythagorean property, the hypotenuse has to be the square root of t of this side squared plus this side squared. That's how we get this. And then we plug into the actual integral and simplify. It becomes a rational expression. Okay, so that's one way to do it, and it's fairly easy. If you understand this diagram here for the triangle, plugging it in, simplifying. Now let's do it another way. I'm going to multiply the numerator. I think I did something similar to this in another video, maybe the last one. I'm multiplying the numerator and the denominator by secant squared of x. Secant squared, secant squared. So that's 1. All I'm doing is multiplying by 1, so it doesn't change it. And now, this is what I'm going to get. In the numerator, there's just 1. I'm multiplying 1, so this is just secant squared of x. And then dx over. And then secant squared times sine squared. Remember, secant squared is also 1 over cosine squared. So when I multiply the secant squared times the sine squared, I basically get tangent squared. So this comes out to then 4 tangent squared of x. And now in the second part here in the bottom here, denominator secant squared times cosine squared, those are reciprocals. So secant squared is 1 over cosine squared. So that cancels out. I get a plus 1 here. And this can be written as 2 tangent of x squared plus 1. And here I could use a substitution and say, okay, let's let u equal to tangent of x. So notice the similarity, but we're not going to have all this over here. We don't need it for this one here, but we do use a tangent substitution here. So du would equal to the derivative of tangent of x is secant squared of x, and this will be dx. So the secant squared of dx right here, that's your du. And the denominator, tangent of x, so we got u equal to tangent of x, then du equals secant squared of x dx. Replace this part here with du, and let's write it this way so you can see it a bit clearer. So this will be 4, and the tangent is u, so this will be 4 u squared, and then plus 1. So then the 4u squared can be written as tu squared plus 1. And now let's do this so you can see it even clearer. Let's do another substitution. You don't have to do this, but just in case you can't see it here, t is going to equal to 2u. So dt, derivative of 2u with respect to u is 2. And this is du. divided by 2, like this. So this du can be replaced by 1/2 of dt. I put the 1/2 outside, and this will be dt. And this would be t here, 2u squared. This would be t squared plus 1. And you see, eventually we get the same thing we did with the other substitution. A different route, but comes out to the same point here. So this would be 1/2, and this would be arctan. In this case, instead of u for the formula here is a t, so this would be 1/2 arctan of t. But what is t? 2u, right there. But what is u? Tangent of x. So this comes out then to 2 tangent of x plus the constant of integration. So again, final answer, same answer we got in the part 1, 1/2 arctan of 2 tangent of x plus the constant of integration. Thanks for watching. We'll see you next time.